Hello again, my name is Devin Cairns, and this is video 4 of implementing subsurface carbon processes at a watershed scale in the reactive transport model BioRT-HBV. And so in this video, we will go over implementing sorption reaction for DOC in BioRT-HBV. And we will first be going over how to implement the equilibrium controlled sorption reaction. In video 5, we will cover a kinetically controlled sorption reaction. So to start out, let's go to the next slide. So in terms of the sorption reaction, this is going to most involve DOC, and most of the time we have a large portion of our DOC being produced and stored in these shallow soils. So a lot of the times DOC will be produced during wet and warm times. However, it'll be stored in drier times, and oftentimes DOC will be stored to the solid phase via sorption processes. And so more DOC tends to be stored in the soil phase where more DOC is produced, so in these shallow soils. Also where we have more mineral phases like clay particles where DOC can sorb more easily to the soils. So in terms of our sorption reaction, we implement this in the shallow soil zone. And so when we run this through our BioRT-HBV model, we'll see how implementing sorption reactions on top of our shallow zone and deep zone respiration processes affect our stream carbon dynamics. So how do we represent sorption reactions within our system? So in terms of this reaction, we are representing it by an equilibrium controlled sorption reaction. So we're really representing this in BioRT-HBV by conceptualizing it as a cation exchange reaction controlled by equilibrium. So we'll have a KEQ value, our equilibrium constant, as well as our products of our reactions controlled by over our reactants. So we have X negative, which is representing our solid phase. So maybe our negatively charged clay particles that attract our more positively charged organic dissolved organic carbon particles, so they can sorb onto the solid phase. And this XDOC, this represents when DOC is actually sorbed to the solid phase. And so we, so our concentrations are really controlled by this ratio of free DOC that's dissolved in our pore waters to the amount of DOC that's already sorbed onto the solid soil phase. Again, the files we will amend to set up this equilibrium controlled reaction are the same as what we have amended for implementing our two respiration reactions. So our chem.txt file, our database file, we'll double check everything, and then as well as our initial condition and our precipitation chemistry files. So the first file we will amend is our chem.txt file. And this is an interesting one because we will have to put in a secondary species for this reaction. So we need to list all of our primary species. And again, we will think back to our reaction, which is this solid phase into our two aqueous species. X negative really represents the solid phase without DOC stored. However, again, this is an equilibrium controlled reaction. So we have these two products. And so in terms of our primary species, we will list X as one of our primary species in our aqueous phase. And since it's an equilibrium controlled reaction, we will list XDOC as our secondary species. And we'll list this as our secondary species because XDOC is a product of the combination of X and DOC controlled by this equilibrium reaction. And again, if you want more explanation of primary and secondary species, I'd recommend viewing some of the other videos, more dealing with some of the chemical weathering processes. Those should explain the primary and secondary species more in depth. However, in terms of setting up this equilibrium controlled reaction, if you set X as a primary species and then XDOC as a secondary species, And then we'll look at the database to see the equilibrium cation exchange reaction that's set up in there to control this. And so we don't need to add anything to the mineral kinetics because it's not a kinetically controlled reaction, it's equilibrium controlled. So again, the only thing we're adding is this X in the primary species and XDOC in the secondary species. And then we will set up and double check everything in the database. And so when we look for this, since it's a cation exchange, we'll look in the exchange portion of the database. So we can see that X is defined as a primary species for a cation exchange reaction. And so that's listed first in the beginning of this exchange. So it's not going to be listed in the very top where the other primary species are listed. It's listed as specifically part of these cation exchange reactions. And so then we have the solid phase or the product of this cation exchange. So this XDOC, which is representing DOC sorbed to the solid phase. We can see that it has two products or two reactants, depending on which way you're looking at the reaction. So we have the X minus, which represents solid phase, and then aqueous DOC and a 1-to-1. And then this value here is our KEQ for our reaction. So it represents this KEQ here. We define it here in our database. And again, we need to set up our initial condition file. And since we've only added one primary species and we are representing it as an aqueous phase, even though this is the solid phase, we set out the concentration in the initial condition file. So again, this is very low because in precipitation, we don't have these solid soil phase available for sorption. However, in the upper zone or the shallow soil zone, we have a higher concentration to represent more cation exchange sites that DOC can sorb to in the shallow soil zone. The lower zone will have a lower concentration to represent less of these available sorption sites for DOC. And again, since this is a primary species, we'll include it within our precipitation file. And again, we should be following good practice. So this X negative should actually be prior to these two solid phases. However, they're all set to the same value, so it should be okay for this one. But again, it's best practice to order them all in the same order. Okay. So now we'll go over and look how we've actually put these into our input files. So we'll go back to our input files. And again, I've already set this up. So Sleepers River equilibrium controlled sorption. And we'll look in our chem.txt file. And we can see that we've listed X as our primary species and XDOC as a secondary species. So that's all good. We will check our database file. And we're going to go to the cation exchange block. So we'll type in exchange to get to the beginning of the exchange block. You can see that X is listed as a primary species for the exchange. And then we can see our reaction here, our equilibrium controlled reaction here. We can see KEQ. Again, this is log KEQ listed in the database, so it's set to -1. So that's 10 to the -1 is what your KEQ value is. Okay. So that's all set up in matches. We will look at our initial condition file. We can see that we've specified the initial condition of concentration for each of our primary species we've added. So that seems right. And then we will double check our precipitation chemistry files. We can see that we have all of our primary species listed. And we can see that they are in the best practice order here as well. So pH, DOC, CO2, then our X negative, and then our two solid phases. Okay, so then we can run that. We can look at the output. So it'd be EQ sorp. Okay, we can see that it's ran. We'll look at our output. Yep, here. Double check. Looks like we have numbers for everything, no errors. Great. So now we can look at our output from this reaction, see how it compares. So on the left is just when we've run the reaction with shallow zone and deep zone sorption included, which is what we covered in our previous video. However, when we implement equilibrium sorption, we can't see a large difference going on at the moment. So what I have done is actually plotted these concentrations on top of each other so you can see smaller changes. So we can see that when we've implemented our deep zone respiration, again, we're getting that flushing pattern happening more from the decrease in our deeper zone concentrations. However, when we implement the sorption equilibrium, we can start to see there's slight differences in the peaking dynamics, or how high peak DOC concentrations go. So we can see that during these wetter times where we have an influx of water and so we can see during these wetter times, we actually have, when we would have more production of DOC, we can actually see a decrease in DOC concentrations. And so that would be driven by the fact that we have this increase in DOC production, and then we also have increased sorption of DOC to the solid phase as well, bringing down these DOC concentrations. And so we can actually see that happening in the shallow zone, how implementing equilibrium controlled sorption kind of modulates the concentrations in the shallow zone based on time of year, how much flow is happening and when it's happening. We can also see that there's a slight change in the deep zone concentrations. And that would be more of an artifact of, since the shallow zone concentrations are changing, what's contributed to the deeper zone will be changing as well. And so that is covering implementing equilibrium controlled sorption, the equilibrium controlled sorption reaction into BioRT-HBV. And this next video will cover, video 4 will cover implementing the kinetically controlled sorption reaction and comparing what the difference is between implementing equilibrium and kinetic controlled sorption reactions, and kind of talk a little bit about why we would incorporate these different types of sorption reactions within our model.